Hello, everyone. Good morning. Thanks for coming. And thank you to the organizers, Quentin. Yeah. Wonderful workshop, and I've been thoroughly enjoying it so far and looking forward to the rest of the day. Right. So I want to tell you a little bit about Gromov-Wasserstein alignment, which is this very interesting problem that is rooted in optimal transport theory, and basically asks the question of how to optimally align or match up probability distributions with one another in a way that kind of best preserves their internal structures. And I'll explain this later on. But I've been quite interested in this framework for probably the better part of like 2.5 years now, because when I first encountered it, Gromov-Wasserstein alignment had a bunch of cool applications to computer vision, single-cell genomics, machine learning, and so on and so forth. But at the same time, it had little to no statistical computational theory associated with it, nor kind of any real geometric understanding of what's happening in the background. And I basically want to share some nice recent advancements we had in this space with you guys. And the results that I'll present are probably spread across 4 different papers at this point. So with a wonderful group of collaborators. So huge thanks goes to Zhengqing, Christian, Yusuf, Barat, Gabriel, and Kengo. And with that, I'll get started. And let me kind of dedicate my first few minutes to preaching to the choir, to optimal transport, just to kind of set up the baseline, the basic ideas, maybe some notations that will come in later on. And I mean, for me, really at its core, this is a question about comparing probability distributions by quantifying the total cost that is associated with transporting or reshaping one into another with respect to a given cost function C. And despite being an old problem due to Gaspard Munch back in the 18th century, I'm showing here the contemporary formulation due to Kantorovich, who writes the problem as this infimized kind of total, I don't know how to navigate this thing. There we go. Total transportation cost when the infimum is over all possible couplings of our 2 marginal distributions, where a coupling is kind of understood as a randomized transportation strategy between them. And off the bat, I want to observe that, and Alessio mentioned this yesterday in his talk, that optimal transport is an LP, is a linear program, which is great because this immediately gives you computational efficiency. We have a bunch of good algorithms for solving LPs. Plus, perhaps even more importantly for this talk, a lot of very powerful tools for analysis that really have been kind of the driver for the very rapid development of statistical, computational optimal transport, Wasserstein geometry in the past couple of decades. And by the way, this same linearity is actually absent from the Gromov-Wasserstein problem. It would be one of the main challenges we'll have to overcome to start making some progress there. But I mean, this is Kantorovich OT, and specializing to a distance cost or perhaps a power thereof gives rise to one of the arguably most interesting objects in optimal transport theory, which is that of the Wasserstein metric. And we take the speed route to get something that behaves approximately like an LP norm. And we call this a metric because it metrizes the space of probability distributions with finite p moments. And this metric space we're getting out of that, which is called the Wasserstein space. I mean, we all know that one of its unique characteristics is that it entails this very interesting and rich geometry that is in many ways very similar to the geometry of the underlying space, the space on which our distributions are supported, let's say Euclidean space for us. Because through this lens, you can basically take a lot of ideas that are natural to think about in Euclidean spaces, such as straight lines or midpoints or averages or even optimization, and lift them to this abstract space of probability distributions, right? So I mean, for example, in the Wasserstein space, we can ask not only how far 2 distributions are, that's your metric, but we can actually also think about the shortest path that connects them to one another, whose length is this distance. These are what we call Wasserstein geodesic curves. And I mean, these geodesics give us kind of a nice and natural interpolation between distributions, smoothly deforming one until you kind of hit the other. And that has a bunch of usages, for example, for shape morphing tasks in computer vision. Now, the moment that you have a geodesic, you immediately get a natural notion of an average of the distributions at the endpoints, right? You just hit the midpoint of this geodesic, and this can be indeed generalized to taking averages of larger classes of probability distributions, like Cesar talked about yesterday, using the notion of Wasserstein-Berry centers. And I mean, as I kind of alluded to, you can even optimize functionals of probability distributions, such as entropy or maybe some notion of interaction or potential energy over the Wasserstein space by running gradient flow algorithms, because this space effectively behaves like a Riemannian manifold. You have a fully differential structure, and this gives you access to this very powerful algorithmic framework of Wasserstein gradient flow. So I mean, all in all, loads of kind of good structure here to try and exploit and tap into. And I think that, in my humble opinion, the reason that OT had such a tangible impact on machine learning in recent years, for example, is because in data science, we model complex data sets as probability distributions over high-dimensional manifolds. And through this lens, you can start reasoning about a bunch of tasks using these kind of abstract geometric manipulations or operations on probability distributions, and in fact resolve these tasks in a very principled and methodological manner, in fact, because I mean, at this point, thanks to the progress in computational and statistical OT, we have efficient and very accurate algorithms for computing all of these guys at scale on real-world data, right? And maybe as a very simple example of that, let me show this mixed style transfer task over here, where basically I give you a content image, a bunch of styles. I want you to mix up these styles and apply the mixed style to the content. So I mean, I want to build an AI box that does something like that. And depending on the intensity of each individual style, you maybe end somewhere on different slot in that grid. And I mean, if you try to black box this, right, just throw data and computation at this task, this is a quite complicated input-output relationship, and resolving that will not be easy. Although if you think about this problem in Wasserstein space, it resolves itself like that because it's basically just a composition of a barycenter with a geodesic, right? So, I mean, to throw the problem, let me show this, into Wasserstein space, we need a way to represent images as probability distributions. There are standard ways for building these types of encoders. You can use pre-trained layers from a VGG network or something like that. And upon representing the individual styles as distributions, we want the mixed style. This is nothing but a barycenter. We assign the weights, describing how intense should each individual style be in the mixture, and compute the barycenter, which represents the mixed style. Then we want to apply this to the content. Great, so we stretch a Wasserstein geodesic between them, choose how much of it we want to traverse, again, how much or how intensely we want to apply the style to the content, get a distribution in between, decode back, and voila, right? That's the stylized content. And I mean, this is completely white box, and this is efficient to implement. You understand exactly what's going on in the background. And if more machine learning algorithms would look like that, that would be great. And this is an actual system. This is called Wasserstein style transfer, proposed by a good friend of mine and a collaborator, Yusuf Marah, back in 2019. But I mean, at the same time, this is a drop in the ocean, right? This is one example in a sea of algorithmic innovation that was driven by optimal transport. So really, very compelling. But at the same time, you know, the Wasserstein geometry and optimal transport-based distances are not necessarily the right figure of merit to have in mind, no matter the application at hand. And at this point, I want to kind of start maybe surfacing. Sorry, what?
Sorry, before going.
Question, yeah.
I have a question,
Yeah.
In Wasserstein space, what property you do like to check, for example, when you compare the images?
Come again?
When you compare the images in Wasserstein space, that you define some properties, right? What property you define for comparing, for example, images? Because we do use like...
You ask how to encode?
Like just comparing images that you have, for example, in such a space. Or maybe just encode.
Yeah, but I mean, I'll compare with Wasserstein distances. So the question is really how to encode, I think.
In this space, is there any property that you define or you have?
So I'm not sure what space you're talking about.
Maybe I can show you that.
Sure. Right, but I mean, so in principle, the moment that I can represent images as distributions, I will compare them in the Wasserstein metric. How to represent them as distributions? So you need to build an encoder, and you could, for example, in this specific application, you extract features using this VGG network, and based on these features, you have some discrete probability distribution. You can compute its covariance matrix, and you just match it up with Gaussians. So all of these would be Gaussians, and then everything is closed form. You don't even need to solve optimal transport if you work with W2 cost. Yeah, all right, good. So yeah, as I started to say, let me kind of give maybe a couple of instances where Wasserstein distances don't quite fit the bill to motivate the notion of Gromov-Wasserstein alignment. And first simple example is imagine you want to interpolate between these two horse shapes, right? A horse in two different postures, representing them as point clouds. And I mean, again, you can stretch a Wasserstein geodesic between them and sample a couple of points along the geodesic to get interpolants that maybe look like that. And I mean, it kind of interpolates, I guess. But there are also a bunch of artifacts here of particles that are flowing along the trajectory that just minimizes transportation cost without any regard to the global structure at hand, right? Trying to preserve this horse shape, because there's nothing about Wasserstein distances that incentivizes them to look at global structure. It's all about, you know, what's my shortest path from source to destination. And this is not quite what we're looking for here, right? If anything, we probably want something that behaves more like a rigid body optimal transport and does something like that. But yeah, Wasserstein distances don't quite give that to us. Another canonical example where Wasserstein distances don't work is when you want to compare distributions that live in, you know, inherently incompatible spaces with no common natural embedding. This is not a great example because all of this lives in R2. But I mean, imagine two kind of separate metric spaces with two different metrics defined on them, right? There's not even a way to write out a Wasserstein distance. Yet the question still stands, is there like a meaningful notion of discrepancy that one can apply in these types of situations. And what I'll try to show you is that, well, both of these instances, as well as a bunch of additional ones, can be holistically treated under the single framework of an alignment problem, which is that of Gromov-Wasserstein alignment.
So
let me
preserve the geometry of these shapes to preserve.
I'll explain. Yeah, just bear with me, and I'll explain. Yeah, cool. Right. So let me talk about Gromov-Wasserstein distances. So alignment is really the canonical way to motivate this idea, where you basically want to learn a matching or a correspondence between heterogeneous data sets, and this comes up in various applications from, for example, shape matching in computer vision, to multimodal analysis in single-cell genomics, to even kind of machine learning translations, although this one is probably obsolete at this point because we have large language models. But I mean, there's a lot of different applications. And in these types of applications, we typically care about two things. First of which, we want to quantitatively compare how similar or different our two data sets may be. But then, perhaps even more importantly, we want to obtain the matching or the correspondence that nicely aligns them with one another. And Gromov-Wasserstein distances are built to basically do both of these at the same time. So let me show you the definition. And maybe I'll use this object matching task as my running example here. Right, so we want to learn a matching between these two geometric objects. We want the matching to preserve global structure, so maybe kind of matching head to head, shoulders to shoulders, feet to feet, and so on and so forth. Now I mentioned the data can be heterogeneous, so maybe we're actually looking at something like that. And with this in mind, first thing that I need is a mathematical model for these geometric shapes, and I'm going to use metric measure spaces for this. So a metric space that encodes the geometry and a probability distribution that captures the, I don't know, density or intensity of your particles or pixels or atoms or what have you, depending on the data that you're looking at. And with that, I can now go ahead and replace these geometric shapes with their metric measure space models, which is kind of cool because it completely abstracts away the application. Of course, you can think about pretty much any data set that you want in this very general fashion. And with that, I mean, that's basically my first ingredient. Next thing that I want is my alignment, which in the language of optimal transport theory is just a transport map. And yeah, by the way, I'm sticking with deterministic maps for the moment, just for simplicity of presentation. We'll stick to we'll switch to couplings a la Kantarovich in just a moment. But I mean, for now, a deterministic function from X space to Y space that rearranges this blue mass into the red one. And I mean, up until here, all of this is very similar to optimal transport. Though here comes the key difference, which is how I'm going to set up the cost function. And the idea is that because I want this T to serve as an alignment, I'm going to impose a minimum distance distortion requirement on it, essentially asking it to preserve the pairwise distance distribution as best as possible, matching up close by points in blue to close by points in red, far apart ones to far apart ones. All in all, you want it to behave approximately like an isometry, right? And so I'm going to set up a cost function that is called the distance distortion cost that will induce exactly that effectively by penalizing for distortion of distances that are induced by this mapping T. And I mean, if you're happy with these three ingredients, then putting them together, again, up to switching from mappings to couplings, gives rise to our quadratic Gromov-Wasserstein distance. And I'm using the quadratic parametrization here. Of course, you can parameterize this more generally, and I'll show this in a moment. But this is the definition due to Facundo Memoli back in 2011, though I've been told that this actually appeared in an earlier conference paper, I think as early as 2007. So yeah, maybe an even older idea. And formally, what's written here is an infimized L2 norm of the distance distortion cost with respect to this pi times pi product coupling. And perhaps kind of morally or a high level, what this really captures is the least amount of distance distortion you can achieve between your metric measure spaces when optimizing over all possible matchings thereof. And off the bat, once again, I want to observe that unlike the linear optimal transport problem, here we're actually looking at functional that is quadratic in pi. Right? Now, first of all, why quadratic? Well, because you have to sample from it twice in order to evaluate the cost. You sample once, you get a point from each space, x, y. Sample for a second time independently another pair of points, x prime, y prime. Now you can compute distances and compare distance distortion, right? So you have to sample twice to evaluate the cost. And as I mentioned before, I mean, this quadratic nature is to a great extent the main challenge in dealing with this problem, because while this has the flavor of optimal transport and is very kind of familiar to us, it doesn't give us direct access to this pool of knowledge of statistical, computational, geometric OT, because many of these tools are contingent on linearity, and it's not present here, right? So this is something we'll have to figure out. But for now, this is the definition. By the way, here's the more general parametrization, the peak youth Gromov-Wasserstein distance, Q serving to exponentiate the distances, whereas P is basically the parameter of the LP norm. And yeah, I mean, for those of you familiar This is actually an LP relaxation of a more classical notion of a Gromov-Hausdorff distance that quantifies how far two metric spaces are from being isometric. And as such an LP relaxation, again, just directly from the definition, a bunch of good structural properties fall out. And first and foremost, this distance is actually guaranteed to be finite, given that these mild conditions, moment-like conditions on our marginal spaces are satisfied. And I mean, this would be satisfied by pretty much any two data sets in practice. So effectively, this gives us this very broadly applicable and robust framework now for comparing pretty much any two data sets that you want, right? It doesn't matter anymore. Euclidean data, graph data, manifold data, all of these are comparable. All of these you can kind of crunch under this framework, which is useful. Then the distance actually nullifies if and only if there exists an isometric transportation map between our distributions, which we can further understand actually in this distance with a bunch of symmetries, a bunch of invariances, right? You can translate your distributions, you can rotate them. None of this would actually change your Gromov-Wasserstein distance measurement, and this is good, for example, for learning symmetries or for graph isomorphism tasks and stuff like that. And much like its Wasserstein counterpart, I guess, once again, you get a metric on the appropriate space, just that here it ends up being a quotient space, a space of equivalence classes of metric measure spaces that are identified up to this isomorphic relationship from before, which, I mean, I personally think is quite remarkable because you start from this completely abstract space of equivalence classes of metric measure spaces, and all of a sudden you get a metric structure, you get tools for analysis, you can start thinking about geometry. And I mean, you know, we don't understand as much about Gromov-Wasserstein geometry as we do about the Wasserstein one, but still, I mean, there's a lot of compelling reasons to try and adopt this as a framework for alignment and mold it into kind of principal algorithms and methodologies, but for that we need statistics and computation. So I would like to start talking about that. And for statistical computation, I have to figure out what to do with this quadratic nature of the problem. And the way we're going to deal with this is effectively by developing a new variational form for the Gromov-Wasserstein distance that will relate it to a certain class of optimal transportation problems. And the moment that I will have this bridge between, I mean, Gromov-Wasserstein, this new problem that I'm trying to understand and learn something about, and Wasserstein, or optimal transport, a well-understood problem that we know a lot about, then I would effectively be able to start tapping into this pool of knowledge and using all this progress on OT to start making some progress on the GW side of things. So that's the idea, and let me show you more concretely what I mean. Now, I'll treat a special case, which is that of quadratic distance between Euclidean metric measure spaces of possibly different dimensions, although at this point we do know how to extend most of this theory to arbitrary Hilbert spaces, to kernel GW, even to Gromov-Wasserstein over constant curvature manifolds, so a sphere hyperbolic space, for example. But I mean, I'll stick with flat Euclidean spaces throughout. And this is my quadratic distance. And the reason that a quadratic cost is nice is because you can expand it, right? So indeed, if I just expand and collect terms, then up to this assumption that my populations are centered, which comes for free because of invariance to translations, I can now decompose this quadratic Gromov-Wasserstein distance into the sum of two terms, where the first one is basically a constant, depends only on my marginal distributions through these moment-like expressions, whereas the second one captures the dependence on the coupling. Again, you can see the quadratic dependence over here. And of course, from an optimization perspective, a duality perspective, if you will, it is only this S2 that is interesting. So that's exactly what I'm going to do. I'm going to develop a variational form for S2. So the goal is to start from this guy and end up at something that is optimal transport-like, keeping in mind that here I'm quadratic in pi, and I want to end up linear in it. And therefore, my first step will not surprise you. I'm going to linearize this quadratic term and replace it with this simple optimization problem over here. I mean, you can easily check that if you differentiate this guy, find the critical point, plug it back in, you go back to the original expression. And by further observing that your optimizer, this Aij pi star over here, actually looks exactly like half the correlation between xi and yj with respect to the coupling pi, then simply by applying Cauchy-Schwarz inequality, I can further restrict myself, or this optimization, to this bounded interval over here, where m mu nu is just the root of product of second moments, which obviously pops up as a result of application of Cauchy-Schwarz, and importantly, gives me a compact domain here that depends only on the marginal distributions, right? So with that, I can now pull the infimum over these Aij's outside, rewrite everything in matrix form, where now this d mu nu over here is the set of all the x times dy sized matrices that are entry-wise bounded by the same m mu nu over 2 constant from before. And once here, I'm basically done, right? Because if we think about this integral as some new weird cost function, obviously parameterized by this auxiliary matrix A that I've introduced, then in this dashed box we have an optimal transportation problem with respect to the CA cost, and this gives me my dual, my variational form, where we've been able to write the second bit in my decomposition of quadratic GW, this S2 guy, as this infimum of a class of transportation problems with a parametrized family of cost functions, where the parameterization uses this matrix A that I've introduced. And so, I mean, Gromov-Wasserstein is not optimal transport, but it is the infimum of such. And this is more than enough in order to start doing some statistics, computation, and even some geometry towards the end. Okay, so that's, yeah, if there's any questions, please.
So you transform the non-convex quadratic coast into a convex one?
Come again?
You transform this non-convex quadratic coast into a convex one?
No, so yeah, so first of all, Gromov-Wasserstein is actually a concave problem in pi. I mean, you can see it from here. And this is not a convex one because, I mean, in A, if you look at the dependence on A, so this, I mean, it's not, you know, it's not an infimum of linear functions, right? Yeah. So, I mean, it's the same problem, just rewritten differently, and importantly gives me access to something that is optimal transport-like.
How difficult is to compute this minimum?
Excellent question. I'll talk about this and explain exactly what we know about computation. But yeah, I mean, computing the unregularized Gromov-Wasserstein distance is quite hard. It's an instance of a QAP, of quadratic assignment problem, which is an NP-complete problem. Yeah. So you have to regularize a little bit to do something. Yeah, much like optimal transport. Yeah, although optimal transport in itself is a much better computational framework, this is a quadratic assignment. Yeah. Any other questions I can take before moving on?
So what did you say? Oh, sorry.
Yeah, sure, good.
I have a stupid question. P and Q need not be exponentially conjugate. They can be whatever.
Yeah, whatever. Sure, yes.
So why do you say it's not convex in A?
Yeah, I mean, this is not a convex function in A.
So there is a quadratic term and a linear term.
Yeah, but you infimize over the pi's. Right, so you can think of this as a function of A, of a class of functions in A, then you take an infimum with respect to the pi. So generally, this is not convex in A. Right? I mean, infimum of quadratics. So you end up with, with something. Yeah.
So A depends on pi? Or?
So, great. So that's a great point. The answer is no. Right? The way that I've rewritten it, and it's very important actually, I mean, if there was dependence on pi here, I wouldn't be able to do much with this variational form. But thanks to this Cauchy-Schwarz step over there, I can effectively decouple the A and the pi, and that's the key for getting a form that is kind of workable for me and can be used to do something. Yeah, great. Anything else? All right, awesome. So let me show you what we can do with this. And I'll start with statistics because, I mean, why not? No, I mean, algorithms, right, will predominantly run on sample data anyway. So I think you have to be able to estimate the distance before doing anything else. And I'm really starting from the simplest statistical question possible, which is how good is the empirical plugin in approximating the ground truth distance between the populations, and hopefully for reasonably sized data sets, we can get a decent approximation. And well, at least asymptotically, we knew the answer in the sense that Memoli in his original 2011 paper showed that empirical plugin is an asymptotically consistent estimator of the distance between the populations, but the moment that you take another step into the non-asymptotic regime and ask for a rate for the error, then this has remained kind of a wide open question with no rates available. And thanks to our variational form, we can now resolve this. We can get a sharp characterization of empirical convergence under Gromov-Wasserstein, and this is the first result that I would like to present. Now I'm showing that the upper bound, we have a matching lower bound. I'll say a few words about it in a minute, but I do want to focus on this result. This is kind of the crux of the entire argument. And as you can see, I'm assuming here compactly supported distributions, and I'm giving a bound on the empirical estimation error that comprises these two pieces. The first one over here that converges at this parametric n to the minus half rate. This is basically a rate of convergence for this S1 bit, this constant part of my decomposition, plus some centering bias that, again, I'll explain shortly. Whereas the second part, the more intricate one that actually captures dependence on dimension, this is your rate for S2. The analysis of this guy is much more complicated and, in fact, hinges on the variational form. But before I show you the main ideas behind the argument, let me just make a few comments about this result. First one is optimality. As I mentioned, this rate is sharp. You can basically produce a simple example showing that, I mean, in general, you cannot do better than this n to the minus 2 over the minimum of dimension. Nothing fancy. I mean, 2 uniform distributions over concentric spheres of different radii. That's all you need. And you can basically reduce this to a Wasserstein estimation question where you get the right lower bound. Perhaps more interestingly is to talk about dependence on dimension here, because, I mean, evidently curse of dimensionality occurs, right? We expect this in these types of estimation problem. We have this exponential dependence on D over here. But at the same time, we do want to observe that it is only the minimum of the 2 dimensions that actually enters the bound, which means that if you're aligning one like high dimensional and super complex data set with a simple low dimensional one, it's this low dimension that will govern the rate, which is good to know. And maybe last comment, that this is very high level, almost kind of at the level of pattern matching. But if you actually compare this to the best available rates for optimal transport, you can see that morally the dependence on the different parameters is very much in line, which is basically to say that from a statistical standpoint, estimating Wasserstein, estimating Gromov-Wasserstein is of comparable difficulty, which is not at all the case in computation, right? So this is something that I would like to highlight. And with that, yeah.
Say the complex data means that the noisy data also covering noisy data.
I mean, it doesn't matter, right? Probability distributions. You can, so long that you can model your data as a probability distribution, it qualifies. Yeah. Yes.
First of all, I think it's a great result. Does it work for Sub-Riemannian manifolds?
No, not quite. So we've just been able to derive I'll show you the argument in a minute. You'll see that in order to get the actual rate, which is to treat the S2 part, I basically reduce the problem back to optimal transport using the variational form. So I have to have this variational form holding in more general settings in order to be able to do something like that. And this is something that we're working on. I mean, so we can treat, for example, at least we can derive a variational form at this point over our arbitrary Hilbert spaces. Naturally, the matrix A in my form will be replaced with some potentially infinite dimensional operator there. And you have less control over these because, again, I'll explain why you need some control. So at the moment, no. I mean, this is the setting in which I know how to prove a rate. I know how to prove suboptimal rates for other orders of the distance, for other PQ values. So this is P and Q are both 2. If you have even PQ, you can still expand some quadratics and get something, but we don't have matching lower bounds. So you get like a suboptimal rate. You can still show something.
I mean, of course, for Sub-Riemannian manifolds, you would take their internal dimension, which is much larger, right?
Right.
You would definitely accept that as a...
Yeah. So I mean, but yeah, I don't.
I mean, I'm not saying it's easy or.
Yeah. I mean, that's a great question, but this is what I know how to prove at this point, at least in terms of sharp rates. Right, so let me give you the main ideas behind the proof. And, well, I mean, we can decompose the distance into the sum of S1 and S2. So it makes sense to try and decompose the analysis as well. But one has to be careful here. It's not just a triangle inequality, because keep in mind that the variational form requires the distributions to be centered, right? Which you can safely assume on the populations, but this need not imply that your empirical measures are centered as well. So, I mean, there's really a centering argument behind this inequality. You translate the empirical measures by the sample means, then you can decompose, but one also has to account for the bias that is introduced by this centering step, which ends up costing this additive n to the minus half term over here, which doesn't change the overall rate, so that's fine. And now we can analyze each bit separately. S1, again, is easy. It's just estimating some moments. You use empirical averages. You can show convergence at a parametric rate. So these two together give the first half of the bound. That's the easy part. Then the remaining question is, what about S2? And this is where the variational form comes into the picture, because using it, we can basically reduce the question of estimating S2 to a question of estimating an optimal transportation cost, which I know how to do, up to the fact that I'm carrying this supremum over the matrices A with me, just from how the variational form looks like. And I mean, this kind of suggests that you have to uniformize your analysis of optimal transport cost estimation in this A matrix. And thankfully, I mean, this family of cost functions is nice enough so that you can actually do that, right? And that's the key. I mean, if it's a more general parametrization by infinite dimensional operators, I'm not quite sure how to go about it yet, right? But in any case, once here, I'm in optimal transport land, which is a well-familiar territory, and I have a bunch of powerful tools for analysis. I have duality-based arguments. I have tools from empirical process theory, if it's covering arguments, entropy integral bounds. I even have low-dimensional adaptivity properties of optimal transport cost estimation to low-dimensional data sets. This is known as the LCA principle, the lower complexity adaptation principle that was derived in Axel Monk's group in the University of Göttingen. I mean, all in all, you put all of this machinery into action, and you can prove this n to the minus 2 over minimum dimension rate that when combined with the other parametric rates gives the overall bound. And again, I like showing this because I think like this is really what I want to highlight. This is the key step. The moment you can put yourself in optimal transport type of framework, then you know how to proceed and you know how to analyze these types of problems, right? So that's the first result about the rate. Now, more recently, we started to think about slightly maybe more refined statistical questions, specifically limit distribution theory pertaining to this Gromov-Wasserstein alignment problem, where the idea is that now I pull my empirical distance out of the expectation, center it by an appropriate population quantity, hit it by a rate, take n to infinity, and ask whether some non-degenerate limit emerges as n grows. And these are usually quite kind of complicated or intricate questions to deal with, but we've been able to treat them in 3 different settings, which is that of fully discrete, semi-discrete, and general subweighable distributions, but when the distance is subject to entropic regularization, and I'll talk about these entropic GW distance in the computational bit in a few moments. But the common denominator here, I mean, the reason that we can treat these 3 settings is because in all 3 we can basically show that the underlying empirical process converges weakly to a Gaussian in an appropriate L infinity space, where this F over here is a function space that usually, comprises some dual potentials for an appropriate optimal transport problem. And the point is that the moment that I can show that the underlying empirical process converges, at the group, we have developed a very robust methodology for lifting this convergence to convergence of the functional. Let me explain how this works. So very briefly, right, we have this weak convergence of the empirical process. What we want to do on top of it is basically some stability analysis of the functional of interest. Specifically, we want to derive its Gateau derivative and also show that it is Lipschitz with respect to the soup norm that is induced by the same F function class from before. And once you do that, it basically gives you access to what's known as the extended functional delta method that is indeed able to upgrade this convergence of the empirical process to convergence of the functional with the same root n scaling, and where the limit actually looks like a Hadamard directional derivative of the functional, which in this case coincides with the Gateau derivative under the Lipschitzness, which is evaluated at the same Gaussian variable at the limit from before. So that's the general recipe, and you can follow it and prove these 3 results. And maybe one last kind of nugget of a fun fact that I want to share with you guys is one small result that I particularly like about this project, which arises in this discrete to discrete situation. And what happens there is that, fine, you can go through this analysis, you end up with some limit that has some horrible expression of an inf soup over functions and matrices of some Gaussian variables and so on and so forth, very ugly. But then you can massage it and effectively show that it is equivalent to the solution of a randomized linear program with Gaussian coefficients, which in itself I think is kind of surprising that the limit of quadratic programs actually converges to an LP. Something has to linearize in the limit, but maybe from a more kind of pragmatic standpoint, we can efficiently simulate this linear program at the limit, which gives us access to applications. And indeed, in the paper, we show an application, for example, of this inference framework to testing whether whether 2 random graph models are isomorphic to one another based on IID observations thereof. And in general, I think this is quite a compelling framework for inference with Gromov-Wasserstein distances. So if you like this type of stuff, check out the paper. But this is pretty much as far as I want to go in terms of statistics. If there's any questions about any of this, I'm happy to take them. Otherwise, we can switch gears a little bit and talk about computation.
So the graph that you mentioned in your paper, is it like a
Come again?
Of the graphs that you are mentioning in your paper?
Mm-hmm.
How many nodes you could use it like?
How many nodes? I think we go up to around 50 or something like that. So yeah, it's not massive, but it's also there's no major computational bottleneck if you adopt the framework that I'm going to talk about next. So I imagine you should be able to scale up, but we mainly wanted to show it as a proof of concept that it actually works. Yeah. Other questions? Cool. So let's talk about computation. Right, so as I mentioned, from a computational standpoint, Gromov-Wasserstein is an instance of a QAP, of a quadratic assignment problem, which is hard, non-convex, in general, NP-complete. And this fact has motivated folks to look at a bunch of computationally tractable reformulations and relaxations of this problem, among which the most popular one is that based on entropic regularization, where as per usual, you hit your cost. I mean, in our case, the distance distortion cost with a scale divergence penalty on the coupling. And the inspiration to do that comes from optimal transportation, of course, right? Where the strongly convex scale divergence penalty serves to actually convexify the originally linear optimal transport problem and gives you access to fast computation using Sinkhorn fixed point iteration algorithm, which is great. And this is a brilliant observation by Marco Couturi from back in 2013, I think he mentioned yesterday. Right, but unfortunately, things are not as nice in the Gromov-Wasserstein setting because our original functional is not linear, it's quadratic. In fact, I mentioned it's concave in pi, so you're regularizing a concave function with a convex regularizer. You don't get a whole lot in return, but thankfully there was still enough structure there so that folks were able to derive various kind of heuristic algorithms for approximate computation based on recursive runs of Sinkhorn algorithm, based on mirror descent type of approaches. But I'm calling all these algorithms heuristic because none of them actually had any formal guarantees associated with them, let alone non-asymptotic convergence rates. And this is the gap that we would like to close here. And again, we will be able to do that using the variational form, which holds just as well in the entropic setting. You just absorb your penalty into OT, getting an EOT instead. And because S1, again, is a constant you can compute offline, this is what we need to figure out, how to solve this minimum over A optimization problem. So for that, let me give the objective a name, call it phi, and start by, again, studying its stability to get a sense of how nice of an optimization problem we're looking at here.
Yeah, Ziv, in OT, we do entropy regularization to get smoothness on the dual. What do we gain on the Gromov?
So give me 2 minutes. Yeah, good. All right. Right, so stability. And specifically, we, in this regard, can characterize the first and second order Fouché derivatives of this objective. Morally, you can think of this as a gradient vector in a Hessian matrix of this map phi. And then we can further get control over the spectrum in the form of upper and lower bounds on top and bottom eigenvalues. And the moment that you have that, then it's basically a mean value theorem type of argument that gives you the fact that this objective is actually L-smooth, which means that its gradients are L-Lipschitz, which immediately gives you access to first order methods, right? With non-asymptotic convergence rates, local convergence guarantees. So this is all great. And if you actually happen to further have convexity, then all of this local theory can be upgraded to a global one. And speaking of convexity, because we now have a lower bound on the smallest eigenvalue, if you just guarantee that this guy is strictly positive, then you get this primitive condition on your epsilon regularization parameter that, if satisfies, actually guarantees that you're looking at a strictly convex optimization problem, which is great. But I mean, regardless of whether epsilon is or isn't large enough to satisfy this condition, you always have the smoothness, so you always have access to gradient-based optimization. And this is exactly what we're going to do. I mean, specifically, I'll propose an accelerated gradient method with an inexact oracle, which is kind of a mouthful. So let me try and unpack what's going on here. And the idea is this, right? So gradient method means that I need to be able to take gradients, which, as I mentioned, we already have from the previous computation. And if you actually look at the gradient of this objective, then using Danskin theorem, you can show that it has the following structure, in particular, depending on this pi A, which is the optimal coupling for this EOTA problem over there, again, with the cost function induced by the current A matrix. And I mean, the moment that you see this, I think that the first thought that comes to mind is great. I'll just run Sinkhorn, get some approximate coupling from Sinkhorn, plug it into this formula, and start iterating, and so on and so forth, swiping the error from Sinkhorn under the rug. But I don't want to swipe. I want to model. That's my motto in life. No, but yeah, this is exactly what I'll model with my inexact oracle, right? So Sinkhorn is my inexact oracle. I query it with a matrix. It gives me back an approximate coupling. I'll assume that it is within this delta precision parameter from the true optimizer pi A. And of course, you can run Sinkhorn for as long as you like to make this delta as small as you wish it to be. But the moment that you have the pi tilde, you plug it into the gradient formula, get an approximate gradient, and start basically taking steps along these approximate gradients with the appropriate momentum correction, so an accelerated gradient method up until convergence, at which point, by the way, you get not only a value for the entropic Gromov-Wasserstein alignment cost, but much like Sinkhorn, you also get a coupling. You also get a scheme, an alignment plan, which is usually the object that you want to get your hands on in practice. And by building on beautiful work that very smart people in the optimization community did in analyzing these types of accelerated gradient methods with an exact oracle, we can further, for the first time, provide formal guarantees for this method. I'm showing here the convex result. So I'm implicitly assuming this condition on epsilon that I mentioned before. And by building on a work by Desprémont from 2008, we can basically lift that analysis to the Gromov-Wasserstein setting to provide a global optimality gap bound. And again, we see a bound that depends, or that comprises two pieces. The first one over here that actually depends on k, which is my iteration count. You can notice that scales like 1 over k squared, which is your optimal Nesterov rate for smooth constraint optimization. So we cannot do better than what this first term allows us to in terms of dependence on k. Whereas the second part is basically the penalty for the inexact oracle that scales linearly with this delta precision parameter from before. And that's the convex regime. You can do all of this in the non-convex case as well, where you still have smoothness. This is building on a paper by Gadimi and Lan from 2016. And you get an algorithm. The rate is slightly slower. You end up with local guarantees quite naturally. But I do want to mention that this algorithm has a nice adaptivity property, which is that it doesn't require your objective kind of a priori to be convex. But if it happens to be so, even if you didn't know it, you do get an acceleration in terms of the rates. And of course, the local convergence also becomes global. So we actually can compute now with formal guarantees. This is the algorithm. Yeah, here's a simple numerical comparison. So this is comparing our fast gradient method in terms of its overall runtime versus size of the problem, right? How many points we're computing Gromov-Wasserstein on across different dimensions, to the smear descent approach by Perrier, Couturier, and Solomon that I mentioned before, that like for years was the go-to computational framework for GW. You can see a full-blown order of magnitude of an improvement here. And I can explain where this comes from, because if you keep in mind, our fast gradient method solves the problem in this auxiliary matrix A space, right? Taking k gradient steps, each of which requires a call to Sinkhorn, whose complexity is quadratic in n, which ends up dominating the runtime in our case. Now, the mirror descent approach, on the other hand, they didn't have the variational form, so they effectively solved the problem in its primal form. And this requires a certain cost tensor update step whose complexity is cubic, which dominates the runtime in their case. Now, I do want to mention that in late 23 came out a nice refinement of this mirror descent approach that can exploit some low-rank structure of the problem if present, which allows them to basically shave off one of these n factors, make it a dimension-dependent factor, and match up this quadratic rate that we achieve. But the fast gradient method is still the only one with guarantees. So if this is important for some applications, this is something to keep in mind. But this is pretty much as far as I want to go in terms of computation. From here, I want to talk about geometry a little bit. But yeah, if there's any questions about this stuff, I'll be happy to take them. Yeah.
So presumably, you also get better statistical rates with the entropic regularization. Is that true?
True. You can recover parametric convergence. Yeah. this is the sub-Weibull. All you need to assume is basically sub-Weibull distribution for sub-Weibull, because the highest order polynomial is 4 in the cost. And yeah, you can use the smoothness, the regularity theory for dual entropic potentials in order to show that everything can be controlled appropriately, and basically, yeah, you have potentials that are Holder functions of arbitrary large smoothness.
Does it get any better in this regime where epsilon is sufficiently large for the problem?
Sure. There is a prefactor that depends on epsilon. I think the larger your epsilon is, the smaller prefactor becomes. But in terms of dependence on A, the rate is just parametric n to the minus half, so that's minimax optimal. Yeah. Good? Right. So let's talk about geometry a little bit. How much longer do I have? Mr. Chair? Okay, so I'll just keep going. You tell me when to stop. 10 minutes. Oh, sorry, I didn't. Okay.
Well, it's a little bit less than 10 minutes, but it's okay.
Okay, thank you. Yeah, 10 minutes should be fine. So, right. I really like this part. It is a bit more technical, especially if you're not familiar with the ideas in the Wasserstein case. But I'll try to parse them as much as I can, and at the end I'll show some pictures that will hopefully make sense regardless. Right, but here's the idea, right? So if Wasserstein geodesics are curves in probability space along which transportation cost is minimized, then Gromov-Wasserstein paths should be ones along which shape distortion is minimized, which kind of seems like a useful idea that is worth some exploring. But because we don't a priori know, for example, what is the Riemannian metric tensor that gives rise to this Gromov-Wasserstein geometry, drawing inspiration from how these ideas actually developed in the Wasserstein case, we're going to start this exploration from a gradient flow question, because it is often the case that if you can characterize the structure of gradient flows, you can kind of eyeball the solution and extract the metric tensor from that, which is exactly what we'll do. And the reason that gradient flows are kind of a compelling starting point is because you can think about them without actually ever knowing how the gradient looks like, thanks to implicit schemes, right? Thanks to proximal point methods. And for the Wasserstein gradient flow, this is the famous JKO scheme due to Jordan, Kindler, and Otto back in 28. And it's their result that as you shrink the step size of this proximal point method, this algorithm indeed instantiates a Wasserstein gradient flow in the W2 space. And I mean, there is no gradient here to be found. So our idea was very simple. Well, great, let's just replace this W2 with Gromov-Wasserstein and see what happens, right? So that's exactly what I'm going to do. Now, you can notice that I'm looking at a slightly different variant of the Gromov-Wasserstein distance. This is called the inner product GW distance, IGW for short. It's basically just the simplest variant to analyze, and this is why we started from that. Now we know how to extend this to full-blown quadratic GW, but yeah, let's just stick with IGW for the purpose of the presentation. And morally, you can think of this as kind of minimizing angle discrepancy or something like that. Still preserves global structure, and by further observing that this IGW is in fact invariant to orthogonal transformations, it really makes sense to consider objectives with the same type of invariance. So pick an F that is orthogonally invariant, an initial distribution mu naught, and take your first JKO step, right? By solving this optimization problem. Now, the moment you do that, you realize that there's actually quite a bit of flexibility here, because you don't end up with a distribution. You actually end up with an equivalence class of distributions, if you will, an orbit of distributions along this orthogonal group. And while in principle you can pick an arbitrary representative, this is problematic in two ways. The first is that it's really hard to get any meaningful analytic handle over the relationship between this arbitrary representative and the previous JKO step in order to prove the convergence of this scheme, which is what we wanted to do. But maybe from a more kind of pragmatic standpoint, we really wanted to end up with a sequence of distributions, with a flow of distributions, not of equivalence classes of distributions, which is, by the way, I think also a very interesting idea to think about, maybe even natural under this framework. But our motivation was basically to interpolate distributions in this new geometry. And so what we do is that upon picking this arbitrary representative, we apply a certain carefully crafted orthogonal covariance transform to it. And orthogonal means that it doesn't change the objective value because of invariance, doesn't change the IGW value because of invariance, but the transformation is built so that this orthogonally transformed arbitrary representative is best aligned with the previous JKO step in the W2 sense. We want to get control over the W2 gap between consecutive steps, and you can do that using these transformations. So really this JKO scheme modified for IGW looks like this. It interleaves these orthogonal transformations with the JKO step. So pick a representative, transform, and take your next step from there, transform, next step, and so on and so forth. And you can see that while, at least in the picture, this red sequence of arbitrary representatives, is quite irregular and hard to get a handle of, the green sequence after the rotations is nice enough so that we have not only control over the IGW gaps between consecutive steps, but in fact on the Wasserstein 2 gaps between them, which gives us access to kind of the later books of Ambrosio gradient flow book. And I mean, there's enough machinery there to be able to analyze this quite general scheme. And this is the main result we get in that regard. So my JKO sequence, mu naught, mu1, and so on and so forth, as I shrink, the step size converges to a W2 continuous curve denoted mu t in the 2 Wasserstein space. W2 continuity comes from these orthogonal transformations that I've described, and therefore the flow follows the regular continuity equation. But importantly, its evolution is governed by this velocity field Vt over here that has this funny structure of an inverse negative operator acting on the gradient of the first variation of my objective. Those of you who are familiar will identify this, by the way, as the W2 gradient of the objective. So really we're looking at the velocity field that transforms this W2 gradient through this minus L minus 1 operator. And this L operator, let's talk about that a little bit. This is what we call the mobility operator. It's nice in many ways. I mean, it transforms L2 vector fields to L2 vector fields. It's linear, it's self-adjoint, it has a finite spectrum. But most importantly, I want to observe that it has a certain globality to it, meaning that even a single direction in the vector field at the output has to see the entire input vector field through this integral form over here, which is quite natural and is in line with the global profile of Gromov-Wasserstein distances. And if you explore this operator a bit further, for example, consecutively apply it to some given vector field, you see that along these applications, it serves to really kind of eliminate angle discrepancy. Again, very much in line with the cost that we're working with. And so all in all, what you end up with here is a flow or a movement in the Wasserstein space whose action is to decrease the functional value, but along directions that minimize distortion to the global shape, meaning that if you started with two particles that have been closed at the beginning, they should stay close throughout the entire flow, at least relatively to the overall pairwise distance distribution. And to, well, maybe concretely kind of connect it back to Wasserstein gradient flows, as I mentioned, this gradient of the first variation a la autocalculus is the W2 gradient of the objective, and with that in mind, we can at least formally identify the IGW gradient as this inverse mobility acting on the Wasserstein gradient. So inverse mobility is kind of really the right tilt to the Wasserstein ascent direction, I guess, if we're not looking at minus gradient, that steers you away from shape distorting directions, right? This is really what's happening here. And as I mentioned, once you have characterization of gradient flows, you can extract the Riemannian metric tensor. This is how it looks like in this case. And from there, you effectively get a dynamical formulation. I mean, something that looks like a Benamou-Brenier formula. I'm not showing it here, but it's the regular integral over time of this metric tensor along an optimal trajectory. I will show you some interpolations under this framework, but this is the main result. Yeah, let me.
So is the reason W2 shows up because you did this alignment, or is it more intrinsic than that?
W2 continuity?
Like the fact that you have the W2 gradient and...
Yeah, this actually I don't attribute to the alignment. The continuity comes from the alignment that I've performed. From the why this specifically arises, I mean, it's a good question. And when you actually look at the kind of discrete versions of these velocity fields or the piecewise constant version, there's a quadratic term, which again comes from the quadratic structure of GW, but it ends up being like an O of tau squared kind of thing that vanishes at the limit. So yeah, I mean, you end up with this, which is maybe quite surprising. But yeah, that's the result. And as I said, let me just show you how this looks like. So here's a simple example of interpolating between a fat ellipse and a tall ellipse. On the left, I'm showing the Wasserstein interpolation, which really looks like kind of squashing the fat ellipse into its tall position. Everything moves in straight lines like you expect in optimal transport. The shape gets completely distorted along the way, right? You pass, for example, through a perfect circle at some point, and that's what Wasserstein Benamou-Brenier does for you. Now, for the Gromov-Wasserstein case, on the other hand, the distance is not allowed to distort the global structure, and therefore it identifies automatically the rotational symmetry and finds the rotation as the shape-preserving trajectory. And I mean, automatic is the key word here, right? I don't tell it that there is a rotation. It's just the profile of the distance that tries to avoid distorting the shape that finds this as the perhaps even kind of right solution to this type of situation. And this is, by the way, the velocity field governing each movement. So again, you can see the rotational profile on the right-hand side. The same happens with more complicated shapes. So I mean, this is a cat versus a rotated cat. I mean, you can see like Wasserstein basically rips it apart and puts it back together at the end. Gromov-Wasserstein nicely rotates. I think this has natural applications to computer vision, to video interpolation, for example. Yes?
General question, like you mentioned this IGW, you essentially changed a little bit the distance it is on the inside.
Sure.
So, like, does this distance actually gives you the same result? Like, so what you
I mean, this is for
like the difference of inner products instead of difference of distance?
True. But morally, it does a similar thing. It morally does a similar thing, especially if you normalize your data appropriately. Yeah. Yes.
I just wanted to point out there seem to be some similarities with some talk I gave a couple of weeks ago. It's not about Gromov-Wasserstein. It was about the sub-Riemannian structure of more transport. The idea being that you are basically controlling the internal degrees of freedom along the flow. For instance, just to give an example, when you have two pictures and you are going to go, let's say, the transport from one flow to the other, if you could register the two pictures against some template, the eyes correspond to eyes, etc., then along the transport, if you can make sure that the holonom is zero, the particles begin and end at places that have labels that correspond to specific things. So basically, the spirit of this sub-Riemannian structure is to not only transport distributions, but transport of particles, but of labeled particles.
Interesting. So I would love to get a reference from you, if possible.
So there are some similarities.
But I have can I ask a question? So you say you pin it down with some reference, labels that.
If you could do that.
How do you do that?
Oh, that's a different story.
Yeah. So I think, okay, maybe one thing that I can say in this regard. I mean, in principle, folks oftentimes motivate Gromov-Wasserstein as Wasserstein between incompatible spaces, or of sorts.
Yeah.
Now,
I say that this is different because you are keeping track of the distortion along the way.
Right, right.
So I'm saying that view of looking at the sub-Riemannian structure has some similarities in the sense that it can probably give some acceleration. You gave some ideas in the middle of trying to do transport and in some ways. Mm-hmm. So I'm saying it can provide some clues to getting shortcuts to what you're doing.
Okay. I would.
I'm not saying it's the same by no means.
No, that's perfectly fine, even if it was.
Yeah. But it has a little bit of a similar spirit in terms of looking at the particles and the distortion.
Yeah, so I would love to get a reference, and if we can chat offline, that would be great. But yeah, I guess one issue that I kind of, in principle, have with thinking about maybe optimal transportation between incompatible spaces, because in principle you could define a cost function on two different x, y's and just like do optimal transport. But this is like, at least in my opinion, a very ad hoc approach. How do you define this cost function? How do you pick it? What is the right cost function between incompatible spaces to kind of induce a given structure? I think in the Gromov-Wasserstein setting, this is built into the framework, and this is why I kind of, I don't know, just a comment that came to mind. Can I have one last minute to actually show the gradient flow? Sorry, thank you. So let me show you the actual gradient flow, not the Benhamou-Brenier interpolation. And this is for negative entropy, right? So which has the right invariance properties. And I arrange my particles on the circumference of the sphere over here. At the bottom, you can see your gradient flow in the Wasserstein geometry. This is like, everything maximizes entropy, explodes to different directions. So basically a diffusion. Now, on the top, I'm showing the IGW gradient flow. And it still has this diffusive profile to it, but a controlled one, if you will. Again, keeping in mind the distance we're working with, if two particles are close to one another at the beginning, they should stay relatively close to one another throughout the entire movement. Actually, unlike the previous thing, which I think has a lot of useful applications, I'm not sure what this is good for. But if anybody has ideas like controlled sampling or anything like that, I would love to hear. But maybe the last thing that I'll say is that we can show that this IGW gradient flow, in fact, decomposes into two components. One is a descent component whose job is to basically reduce the functional value, and another one is a damping component that is there to basically steer you away from shape-distorting directions, and it is the sum of the two that gives rise to the overall movement. So yeah, that's my last slide. Maybe I can skip the summary for the interest of time. These are the papers that I've covered if you want to check them out. And yeah, chat about that. I would love that. And with that, I'll stop, guys. Thank you so much for listening.